So now we are going to a more advanced topic. We have been seeing that we have the tail current, which is ideal. What's the meaning of an ideal current source? It has a constant current, infinite output impedance. Yeah, constant current regardless of the output voltage, right? But now I don't have an ideal one. Unfortunately, I have something called RSS, which is large, but not infinity. This is large. Okay, let's see how it is going to affect the performance. The point is IDS still constant? When RSS is infinity, when you have ideal current source, IDS is always what? ISS over 2, right? Look that I have a common mode output. They have the same voltage, not differential, okay? Right. So let's go to KCL. IDS1 plus IDS2 equals to ISS. That's it. What else? Plus IRSS, which is VP divided by RSS. And you can appreciate again, if RSS is infinity, this term is gone. Then I always have IDS1, right? Now, but IDS1 and IDS2, are they still the same, however? Do you think they should be the same or they should not? Why? Yes, and then they are still symmetric, right? Everything else is symmetric. Yeah, I need to bleed more current to RSS, but we contribute the same amount because we see the same thing, right? Again, due to the symmetry, right? Because I'm applying a common mode, I'm not applying differential mode, right? So as a result, IDS1 equals to IDS2 equals to ISS divided by 2 plus VP divided by 2RSS. So it's no longer constant, right? Because so not constant. Right? Because as we said earlier, the reason it was constant because VP will go up with the VG. And now your VP goes up, then this part will be larger, right? What? I cannot read my writing. Because VP changes when VCM changes. Okay, make sense? Now, although this is not differential pair, so I definitely cannot use virtual graph. But however, I can use half circuit. Because they go up at the same time, right? I can chop this into a half circuit to study what the output will be. So the equivalent circuit is going to be I use half circuit technique, but not virtual graph. Okay, so I can draw this circuit as this. This is VDD. This is RD. And this is V out. And this is VCM, because the left get VCM. And this is P, but then it's connected to a resistor. Okay? But how should I chop this resistor now in the lab? I want to make it symmetric.
You shouldn't chop it.
I should not chop it. So last time I have a resistor like this, right? And last time when they're in this direction, right? I chop here. This time, how would you chop it? If I can only allow you to chop it.
Vertically, but that would mean.
Now means I want to chop it horizontally, right? So what does it mean? It's right if you really can zoom in and chop it. It's because this resistor, RSS, is the same as two resistors in parallel, but with what value? You double it. 2RSS, 2RSS. Okay, so when I chop it, now this time I want to chop it in this way, right? Then what do I get? 2RSS. Is this okay? A little bit confusing. But the point is that I try to change this into two symmetric parts, two identical parts. Then I have this. It just actually pretty normal. You have the water pipe going from here to here. I want to split it into two parts so they have the same amount of water resistance. Then both of them need to be thinner. That's why I chop it, right? And thinner means larger resistance, right? So that's why I have 2RSS. So this is the equivalent circuit. Why it is equivalent? Because left and right you put in the same thing. So I can split them. You will have the same result, right? Okay. So based on that, what is the common mode gain? I mean, what is the gain? So now, sorry, I'm jumping a little bit. So my goal is to ask, what is the so-called common mode gain, which is defined as V out divided by VCM. Basically, now I'm not applying differential signal. Apply the same signal to left and right. Both increased by 10 millivolt, both reduced by 10 millivolt. And I want to ask, how does the V out 1 and V out 2 change? I'm not looking at the differential signal. I just want to say how they go up and go down. That is V out divided by VCM. And based on this circuit, what do I see? It must be common source with degeneration, right? It is GM 1 RD, and let me just ignore the channel length modulation, divided by 1 plus GM 1 2 RSS. Okay, so we are seeing a situation that before the common mode gain was 0. Remember, I showed you earlier. When we change the common mode, this one won't change because this is always ISS, right? Because the voltage here is what? ISS divided by 2, sorry. This voltage is always VD minus ID1 times RD. If your ID1 is always ISS divided by 2, this voltage won't change, right? So even you have this noise in the common mode, I always have the same output. But now I don't have ideal current source. I have RSS. Because of RSS, actually I'm going to see the voltage to change when VCM changes. If RSS is infinity, means this is ideal current source, then this is 0. Again, I don't have gain. Right? So this is, yeah. If RSS becomes large, right, then you get a lot of gain, right? And what is the extreme case when RSS equal to 0? Then this is just a common source amplifier. And then you lose the benefits of differential pair to reject the noise due to the common mode here. We still can reject the noise from the VDD, but the noise from the VCM cannot be rejected, right? So if we have ideal current source, you see that even I have a lot of noise at the common mode, I still don't have any change in the output. Okay, so this one is tell you the effect of the tail current At the same time, is the skill of doing the equivalent circuit. Yeah.
So in your previous examples, you didn't have RSS in the way you arranged it here. So that means in your previous circuits, VCM, the noise from VCM will be drastic.
Yes, because here we assume ideal.
Got it.
Then you always have ISS divided by 2, right?
Okay.
So this is going to be constant. Good.
This is why we use the current mirror
Current mirror
for the differential mode circuit that we just did in the previous lab.
to get this one. Yeah, but even you have, but current mirror is to save you from making a constant current source. But here, if you don't do it well, even for current mirror, you still have a small RSS. For example, if you only have a what do you call the one transistor, then it is just R0, right? So later we will try to do degeneration to increase this RSS. But let's take a look what is the problem here, right? Or actually not a problem yet. Now, if I have common mode noise coming in, this is noise coming from common mode, right? So if I have ideal current source, right, despite my input, this is A, so this is VA. This is, what we're doing here? Say again? We don't say that the magnitude here is just as much as we can, right? In ideal case, even it's very large, it should get rid of that. Yeah. I'm actually sorry this figure has some problem. We actually need to add a source here. VA as the input. We in one small signal input. And then add another one here, V in 2, which is VB. So they have a differential input. So again, this is a common mode bias. And then we have noise due to the common mode. But then on top of it, we apply the differential signal, right? So we have VA. When you apply this differential signal, VA and VB, do you see that they are going to opposite direction? But they have a lot of ripple. This ripple comes from the common mode noise. Is that okay? Because an ideal one is that you do have this common mode, and then I have this VA and VB going in, right? But now your common mode is fluctuating. So as a result, my signal is also fluctuating. Now, if this is ideal, because of the common mode rejection, because of what we just discussed earlier, if this is ideal, you always have the same current. So even you are fluctuating, the output have a constant output common mode. So you have a very clean signal. And then if you find the difference, of course, they're still clean. And that's why you can reject the common mode signal. If you have non-ideal current source with RSS, as we just said, when you have a fluctuation in the input common mode, the output common mode will change, right? Output, which is V out 1, V out 2, common mode, fluctuate. They fluctuate due to the noise coming from the gate and from the gate, okay? But luckily, we only interested in the differential output. Differential is this one subtract this one. And because the input are fluctuating at the same time, so the output common mode also fluctuate at the same time. So we still have a clean signal in this case. Right, so I don't know if I explained clearly, but if you understand this slide, then you really understand what we are doing here, right? Basically, just again, let me say one more time, we see this differential amplifier as a bias, constant bias. You always need to bias the circuit so that they are at saturation, right? And then we need to apply the differential signal to it. They go in the opposite direction, like this. The question now is, what if your bias has noise? Your battery has noise. How is it going to affect the output? I don't want to amplify this noise. When the RSS is infinity, means I have ideal current source. We already know that this common mode is not going to change the output because I have the constant current going down. Even you fluctuate the gate voltage, I still have the same constant current. So I have very clean V out 1 and V out 2. So my differential signal is also clean. But if you don't have an ideal current source, just from this line, we see that I'm going to get some fluctuation at the output common mode. Fortunately, left and right fluctuate at the same time because the noise comes from both left and right. So if you only care about their difference, that's why we do differential signal, then it is still clean, right? So we reject the noise from here also, and similar from the VDD. Okay? But what if we have another bad situation? They are not absolutely symmetric. On the left is RD, on the right is RD plus delta RD. Is this possible? Two different resistors, you cannot never make two people identical, right? Same, you cannot make two transistors identical unless your transistor is only an atom, right? Your resistor is only an atom. Then they are identical. But how about their biasing condition? They might not be identical. They are just different environments, right? So this is fabrication variation. But recognizing this source, you will try to make them as similar as possible. Make them very large in terms of size. Make them close to each other to see the similar environment, right? You can chop the transistor, the left, into 4 parts. So this part is on left corner and bottom left corner and top right corner, connect them together. Another is left top corner and bottom right corner, connect them together. They feel the same gradient in the process. Yeah, question?
Simply measuring two resistors to be very close to the same resistance won't necessarily mean that at different frequencies they'll be the same, or does it essentially move?
Oh, okay. So will the frequency change? I think, yeah, if the frequency is high enough, they might not be the same, right? So when you want to claim that they are the same, you need to say that they were when they were at the current and frequency operating condition that you are trying to work on. Yeah, that you need to measure that. Yeah. Okay, so with this, right? So my question to you, when there is a change in the common mode input, right? The noise. What will happen to the ID1 and ID2 in this case? When there's no differential signal. It will change, right? So, but basically this is just a transconductance, right? Your ID1 is going to be equal to ID2. I'm talking about small signal, ID1 equal to ID2 equals to the GM of the circuits times VGS. Not VGS, times VG. Yeah, times VG. I should not say VG times Vin. That would be better because I'm talking about the transconductance of the whole circuit. You see what I'm talking about? We were doing this half circuit, right? I want to know the GM, right? How this ID1 changes with this Vin, right? So it's the overall GM times the Vin. Okay? Make sense? Or maybe to be more clear, I will call this I out equal to ID1 equal to ID2 equal to GM times Vin, right? And then I will just call this ID. What is the GM of this circuit? This is just the GM of the transistor divided by 1 plus GM 2R SS, because this is a common source with degeneration. This is common source with degeneration. The GM, just like we discussed in Cascode, is GM1 divided by 1 plus GM1 divided by 2R SS. Make sense? But what is V in this case? VCM. Very good, right? So if I try to increase the VCM by something, then I will get a change in ID by this much. Well, both of them are changing, right? So isn't that is great? Nothing happened. If I only care about the differential current, correct? But how about the output? Vout1 minus Vout2 equals to Vout1 is negative ID1 times RD. I'm talking about small signal, right? Or you can think about this VDD divided by capital ID times RD, right? But this is just negative ID RD. Basically saying that the voltage of Vout1 reduces when your ID increases times RD.
Is there a RD message?
This one, because I'm doing the currents, not the voltage output. That's GM. Okay, let me, I think this is a little bit confusing. Let me go this. V out equals to VDD minus ID1RD. Do you agree? So delta V out means the change of V out, right? That was the total signal equals to delta VDD minus delta ID1RD. You also agree, right? I just applied delta to the equation, right? What is delta V out? It's small signal. I just call it V out. Just small change of the total signal, right? And what is delta VDD? 0, because it's constant, right? And I assume RD does not change. So this is just RD ID1, right? This is small signal. Right? So I'm jumping a little bit directly to the small signal. That's why VO1 equal to negative ID1 times RD. How about Vout2? What is that? Can you tell me? What is Vout2? Same thing, negative ID2 times RD plus delta RD, right? But we already say that ID1 equal to ID2, right? The change, ID1 equals ID2, right? So as a result, Vout1 minus Vout2 equals to, what's that? ID times delta RD. But what is RD? We just studied before, right? It's GM1 over 1 plus GM1 2R SS times VCM. I'll copy this one, right? And then the whole thing times, that's very bad. I just put here delta RD, right? The whole thing times delta RD. Delta RD is this one, and ID2 is this one, right? So if I assume this is large, then the GM1 is going to get cancelled, right? So what do I get? Then I will get V out divided by VCM, right? This is V out divided by VCM. equals to delta RD divided by 2RSS, right? So let me say again, maybe confusing. What I'm trying to find is that what is the differential output when I have an input at here? This input apply to both the gate and both sides of the gate. And then the first thing I show you is that the current does not, they will change by the same amount. To find the current, I use the transconductance of this common source with degeneration because I use half circuit technique. And they change by the same amount because the current is not affected by the loading resistor when I have infinite output impedance. I don't have channel length modulation, right? So I get this equation from common source with degeneration. And I try to find what will be the difference of the output voltage. The difference of the output voltage, I can just do it by the small signal current times the loading. I just find their difference, and I find out the difference of the voltage is just equal to delta RD times this term that I get here. And then I try to rearrange the term because VE1 minus VO1 minus VO2 is just Vout, the differential one. I take VCM to here, cancel GM1, then I get delta RD divided by 2RSS. Basically, this is saying that I have a common mode input, which I don't want. I want to amplify the differential mode, but I have a common mode input. Because of this non-ideal current source, and because of the variation and resistance, I get a differential output. So basically, I don't have signal going in, but I'm still hearing the humming noise, for example. Right? I did not have any input, differential input, but I get a lot of differential output. Yeah, question?
What did you do?
Yeah, thank you. So I did not say clearly because I assume 1 is much smaller than GM1 times RSS2. So I ignore it. Make sense? Did I answer your question? Yeah. So this is gone, then I can cancel GM1. Then you get delta RD, right? Assume. Exactly. And now, can you tell me when RD is very small, what does it mean? When delta RD is very small, sorry, it means they are exactly the same, right? Or when RSS is very large, what does it mean? It means you have ideal current source. Then you go back to the original case, right? So this is a very good way to check whether you derive the correct thing, right? Okay. This is an example. So what is the common mode to differential mode gain? Basically saying I have some junk noise coming from the common mode, and I really don't want to get signal out of it because that is not the signal I want. What is the common mode to differential mode gain in this case? Well, I can give you the equation from the last slide. I still remember that it is delta RD divided by 2RSS. Let me check. Yeah. What is delta RD here? Delta RD. What is 2RSS here? Think carefully. Can you just say R01 plus R1? No. Think carefully. You're supposed to solve the small signal model, but can you match to any circuit you have learned? What type of circuit is this? What type? Degeneration. Yeah. It is not. It's not a CS with degeneration amplifier. However, when we find the output impedance, we need to ground the input anyway, same as here. So this is just equals to R01 times 1 plus GM1, R1 plus R1. That's it. Yeah, and then you plug in, right? So now go back to the question you said. This is also a current mirror. But we don't just put M1. You need to have more complicated current mirror. But now I have a much larger RSS instead of just R01. Okay, good. Remember, this is called common mode to differential mode gain, right? Well, our goal is that you give me a differential signal. I want to amplify to get a differential signal. That is my goal. When I say something, you go to the microphone, and then it becomes what I want to amplify. But now you have some noise due to common mode. I don't want to amplify. That's why I want to have a really large common mode to very small common mode to differential mode gain. But in reality, what you care is not just the common mode to differential mode gain. What you care is that your differential mode gain is much larger than common mode to differential mode gain, right? So it means that I want to amplify the useful signal a lot, but try not to amplify the noise from the common mode. That's why we have something called common mode rejection ratio, which is basically just saying that what is the gain, or what is the ratio between the differential mode gain and the common mode gain. Is that okay? That's it, right? Because our goal is to amplify the differential. So let's look at this circuit again. I have the common mode biasing, 2 volts, 3 volts, whatever. And then I have the differential signal. I want to amplify ADM equals to V out minus V out 2 V out 2 minus V out 1 divided by V in 2 minus V in 1. That is the differential mode gain. But the common mode to differential mode gain is V out 2 minus V out 1 divided by VCM. Okay, you have fluctuation at VCM. You give me some signal. That is not what I want. I want this to be small. And you give some real signal that you want me to amplify. Yes, I want to make it large. That is the ratio. Okay, so let's look at an example. Like this circuit that we just saw before. What is the differential mode gain? Now, when we do the differential mode gain, we can just assume this is ideal, because it will be very complicated if we not try to no, we don't need to I mean, it will have some effects, but let's just assume this is a constant current source, right? Yeah, because you don't assume this, then it will become a common source with degeneration. That would be troublesome. We just assume it is ideal. So what is the gain of this circuit? Particularly, we also assume there's no variation, right? When we find the differential mode gain. So what is the gain of this one? Yeah, and because it is differential, so I don't care about the sign now. I will just write GM RD parallel RO. Okay, this is the gain, right? We have, right? Where we ignore delta RD and assume ideal current source. Yeah, and free, right? Okay. Now, how about the common mode to differential mode gain? It is delta RD divided by 2RSS, right? Which we just found in the earlier slide, where our 2RSS is approximately equal to R01 GM3, not R03 GM3, RSS. Why do I know that? Because I'm very familiar with this equation, but if you try to do this, this is approximately R01 GM1 R1, right? For this term. But now this is called free. I mean, this is called free. That's why I changed to free, right? So the common mode rejection ratio is just equals to GM1 RD parallel R0, and then divide by the whole thing, delta RD, 2R03, GM3, RSS. You see that for a well-designed transistor, they're really huge. Do you see that? Because delta RD is small, and all these are big terms, which is good. We want to have a large common mode 2 rejection ratio. Say again? Okay, thank you. To be specific, you are right, GMD-R1. Okay. I want to show some here maybe next time, right? Maybe I will save this for next time. It's 45 already. But we basically finished the differential signal.